Now, there's just one more topic here, which just deals with the fast. We're going to redo this lesson. Let's see if we can do it real quick here, just with a couple more confidence intervals. The only thing that happens here is that you don't know the population standard deviation. You have to use a sample standard deviation. And sample standard deviations vary from sample to sample. And sometimes they're bigger than they need to be, and sometimes they're smaller than they need to be. And we don't, if your standard deviation from a sample comes out too small, then your margin, you just have to look at the formula for the margin of error up here. It's this one. If the standard deviation that you get from a sample comes out too small, then your margin of error is going to come out too small. It's a real, you know, if it's coming from a statistic, it's going to vary. So if your margin of error comes out too small, then you're not going to be right 95% of the time, like you're saying. The problem of the standard deviation coming out possibly too small and the margin of error coming out too small means we're going to have to correct for that problem. So it's a little theoretical. You're not going to be tested on the theory really, but let me just kind of punch through 7.6 with you guys to deal with this issue of not knowing the population standard deviation. So this says confidence interval for a population mean when the standard deviation of the population is unknown, which is most likely to be the case. So I was going to go ahead and read this. It says, we've learned to compute a confidence interval for a population mean mu, which is what we just did, when the population standard deviation is known. When the population standard deviation is unknown, we have a problem. In this lesson, we have to solve that problem. Okay, so to compute z-scores of sample means, we use this formula. The z-score of a sample mean, you would take the sample mean and subtract the mean of sample means. Oops. The mean of sample means, which is the mean of the population, okay, divide by the standard deviation, or also called the standard error of the sample means, okay. Now to step back, we know that the mean of sample means is the mean of the population you're sampling from, and the standard error of sample means is the population's standard deviation over the square root of the sample size, and that's what we're using to compute the margin of error down there. This formula has one variable that changes from sample to sample, so one variable that changes from sample to sample, and that's the sample mean. X bar is the only thing that changes when you change your sample. It's a given sample size. As this varies, the z-score varies according to the standard normal distribution, which we've drawn many times. It's the bell curve of z-scores that is a little special because the mean is 0 for z-scores and the standard deviation is 1. That's only when you take the z-scores, okay? If we don't know the population standard deviation, then you can't do that computation. So we have to estimate it with a sample standard deviation. So this z-score for standardizing, so that you can use the standardized or the standard normal distribution, that computation cannot be done for standardizing to the standard normal distribution. Because the population standard deviation here in the denominator, that thing's not known. Okay, and I'm wiggling it around. It doesn't, you don't know its value. So instead, you have to use the sample standard deviation. So S is the symbol for the sample standard deviation. Okay, that's what we use in practice. Now, here's the problem. Before, the formula had one variable, okay? The formula now has two variables, okay? X bar varies from sample to sample, and S varies from sample to sample. There's two things varying there, and now the possible outcomes for the statistic are more variable. You get more outcomes. Two varying values in the formula causes additional variability. How does this affect the distribution of the above statistic? The distribution of possible values gets wider. So the standard deviation is larger. I'll say is greater than 1, which means it's not a normal distribution. Okay? So down below it says the additional variability is caused by the sample standard deviation. The variability in the sample standard deviation depends on the number of deviations from the mean that are random. How many deviations in a standard deviation are random? Ugh. Now I'm going to have to go back. So I'm going way back to chapter 2. I think it's 2.6. Nope, 2.5. Still in this handout. Okay, so here's 2.5. It's not 2.5. Where is it? Ah, here we go. Where we were doing the standard deviation. Okay, here we go. We started by averaging deviations from the mean when we were trying to develop standard deviation. So we had values and we had a mean, and we were trying to figure out how much every value deviates from the mean. And one of the things we learned is that when you add up the deviations from the mean, they always add up to 0. Okay. And here there were 12 values and 12 deviations from the mean, but because they always add up to 0, the last one always has to be the number that makes the total 0. So while there are 12 values, only 11 of them are random. So we say they're n values, but n minus 1 of them are random, and those are called the degrees of freedom. Okay, so going back to our lesson, it says, how many deviations in a standard deviation are random? Well, there are n deviations. Oops. Okay, n minus 1 are random. Those are the degrees of freedom. Now let me put that down below. So n minus 1 is the degrees of freedom, okay, which we usually just say df. Okay, the distribution of that statistic varies according to what family of distribution. It's called student's t distribution. Student is the name of the guy who invented it. It wasn't really his name, it was his pseudonym, student's t distribution. Okay. Y student, it's named after William Gossett. Studied yeast. For who studies yeast? Well, bread makers and beer makers for Guinness Brewery. in the early 1900s. And just making beer. Invented it, but published under this pseudonym. How do you spell pseudonym? Pseudonym, I hope. Student. The company, it's just one of those things, when you do work for a company, they own your work. And they didn't want him taking credit for it, even though he did it, they owned it. Not unusual today, still. Okay, any questions? So that's students' t distribution, and I should say, the variability in the standard deviation depends on degrees of freedom. The less the degrees of freedom, the more the variability, because your statistics are less reliable and you have smaller sample sizes. So you see, when the degrees of freedom are really low, the t-curve has a low middle and heavy tails out here, just because it's more probable that you get wide variability with small sample sizes and low degrees of freedom. So the degrees of freedom indicate the width of the distribution, but do notice that as degrees of freedom increase, the t distribution is approaching the normal distribution, which is the highest one there, where its most probable value, the more probable values are in the middle. For the normal curve, they get pushed a little bit outward with the t distributions because of that added variability. So down below it says, as the degrees of freedom increases, the t distribution approaches the normal distribution. The margin of error in a sample mean when sigma is known is E equals Z alpha over 2 times sigma over the square root of n. We've already done that with a confidence interval. If sigma is unknown, instead of using the Z distribution to get critical values, we're going to use T alpha over 2. And we're having to use a sample standard deviation and divide by the square root of the sample size. So it's really the same computation. But you're going to get your critical T alpha over 2 instead of Z alpha over 2. I'm using a sample standard deviation now. You still have the level of confidence here in the middle of the distribution. Okay. Alpha is still 1 minus the confidence level. Okay. And alpha over 2 is the area of the tails, and then your critical values are called T alpha over 2. Okay, and it's just the number of standard errors that you have to go out to capture, 95% of the population or 99% of the population. And those ones that are captured, those means that are captured by that will be within the margin of error of the population mean. Okay, so we can go ahead and just do examples now. All right, so go ahead, the gather and check. It's the same rules. You still need the sample means come from a normal distribution. So we need for n to be, this is the check. Okay. We need to check that n is greater than 30 or the population is normal. You'll need your X bar value, you'll need S, you'll need N, and you'll need the level of confidence. And then don't forget alpha is 1 minus the confidence level. Okay. Your lookup is going to be T alpha over 2 now, not Z alpha over 2. Okay, and it's still table A2, where in the degrees of freedom column, you now know that that needs to be your sample size minus 1. You still go alpha 2 tails and down like this to the value which we will now refer to as T alpha over 2. So you're not going to the bottom row of that table anymore, where the Z-scores are. Maximum error is easy now. It's E equals T alpha over 2 times S over the square root of n. So it's very similar to what we did before. The endpoints of the confidence interval are just X bar minus the margin of error, less than mu, less than X bar plus the margin of error. Like that. And the interpretation is identical as before. We had said we are a blank percent confident that the mean of something is between two numbers. Blank and blank. Okay, so it's super easy. And honestly, you'll feel like you're doing the same thing as the last lesson. Okay, so let's just do one real quick. It says the mean sleep hours for 35 students. Okay, these are statistics students. N is 35. This is bigger than 30. That's our rule, so we put the check mark down. We have tracked. X bar is 6.4. That's the mean hours of sleep for statistics students in LSAC. And the sample standard deviation, it says that these students, these 35 students, have a standard deviation of 1.6. That's from them. This is a sample. So this is the sample standard deviation that I'm putting down. The confidence level is 0.96. So my alpha is 0.04. Okay, 1 minus 0.96. Now we can go to table A2. Now we use degrees of freedom because we are using S instead of sigma. Degrees of freedom are n minus 1, which will now be 34. Remember, n is 35. Look up alpha equals 0.04. Make sure it's 2 tails. Okay? 34 degrees of freedom, which measures how variable the sample standard deviation is and takes that into account for the margin of error. Okay, I'm going to pop over real quick 34 and 0.04. Here's table A2. Clear it up a little. Okay, so going to 34 degrees of freedom, way down here at the bottom, and make my mark with that. Okay, so 34 degrees of freedom, 0.04, 2 tails. This guy? I hope. So I see, I'll double check it, but that's a 2.136. And again, 0.04, 2 tail, 2.136. Good, you guys, good job. So that's just straight from the table, straight look up. 2.136. Okay, and now the margin of error. It's just T alpha over 2 times S over the square root of n. So that's a 2.136 times 1.6 over the square root of 35, I think. So I'm hoping you got what I got, 0.57. I'm going to do 2 places because the mean has 1 place. So 0.58 really, 0.58. Okay, and now just confidence interval. So X bar minus E less than mu, less than X bar plus E. Okay. So when you subtract X bar, that's 6.4 minus the error, which we're giving a 0.58. So on the low end, I'm getting 5.82. Less than mu, and now adding X bar again is 6.4. And you're doing plus 0.58, which is 6.98. And these are hours of statistics students at NASAC. So we are 96% confident, assuming it's a random sample. Maybe it says it is. So we are 96%. Nobody's going to do 96%. They'll do 95. But we're just, it helps us learn how to use these tables. So we are 96% confident that the mean hours of sleep for what population? Well, Mount SAC stats students is between what did I say? 5.82 and 6.98 hours. It's too precise, but we'll leave it for here. And it's 11:35. Let's do another one. I think we can. 5 minutes. Let's go. Okay, and that'll finish it for the day. So on this one, it says we got 51 women. Fine. N is 51, which is bigger than 30. So check mark. Okay. The mean weekly salary is $726. All right, that's X bar equals 726. Okay. With the sample standard deviation, it says sample S equals $185. 185. I like it when everything's a whole number. Now it says give a 95% confidence interval. All right, so the confidence is 0.95. So alpha is 0.05. Okay. Table A2. So degrees of freedom. You're going to go down to 50. How convenient. N minus 1 is 50. I think it used to say I think it used to be 49 and they changed it so that it would be on the table. Just pick the closest. If you don't see your degrees of freedom, just pick the closest one. The alpha is 0.05 two-tail. Okay. And if you go down to that, ooh, J-Zarco, 2.136. I'm going to prove he's right. Okay, so 50.05, oops, 0.05 two-tails, if I can find it. That was way down there. Oh, wait a minute. Did I screw up? That 0.05 two-tail. I didn't get what you got. Maybe that's an old one. That's probably old. Agreed, 2.009. Maybe that other one was from the last one. 2.009 with a 0.05 two-tail. Okay, fine. So this guy is 2.009. Then our margin of error is t alpha over 2 times s over the square root of n. Let's put in the numbers. That would be 2.009. Yep, 2 standard errors in the margin of error. S is 185. And that's over the square root of 51. Okay. Okay, checking everything. Looks like 52 point, I'm just going to say 52.0 because I'm going to do one more place. 52.0. So when we do x bar minus e less than mu less than x bar plus e. So you're just going to do x bar was 726. 726 minus 52. So that's 674. I'm going to say 674.0. Less than mu. Less than, and we add them. It's 778. 778.0. I'll just, it's 0.0. I'll just refer to dollars now. I'll say we are 95% confident. That the mean weekly salary for U.S. women is between 674. I'll just say 674. No point in saying 0.0. You could say in 0 cents, but what's the point of that? So between 674 and 778. Okay, and that's it. 11:40 exactly. All right, you guys. Got my office hour in 5 minutes, so feel free to join me, and I'll be talking to you. Take care. And my office hour is in a different Zoom meeting, you may remember. Jay Zarko, I think you should include units. Remember, you're trying to explain this to people, so, I mean, obviously dollars on this one, but yeah, I think you should include units.
Professor?
Yes.
When do we take next exam?
Well, it's on the schedule. So let me get this real quick. I have to go over to Canvas and I'll just read it to you so that I'm not going to drag you over there. It's on the syllabus also. So for this class, the syllabus says May 22nd. So that's a ways off. Is that all right?
Okay, thank you.
All right, take care.